MRI, and it is my pleasure to introduce Dr. Mark Griswold. Mark got his bachelor's degree in electrical engineering from the University of Illinois. Then he went to Harvard Medical School for a number of years before he went to the University of Würzburg in Germany in 1999, I believe, to get his Ph.D. in biophysics. He came back to Case in 2005 and is an associate professor in the Department of Radiology with joint appointments in biomedical engineering and physics. So Mark is here today to talk about his research, and in particular to talk about magnetic resonance imaging. So without any further ado, Mark.
Thank you, Ken.
You're very welcome.
Thanks all of you for showing up. Welcome back to school. Hope it's a great productive year. I'm going to talk about MRI, which is what we do across the street in our lab, and in particular two applications or two research areas, compressive sampling and some high-power RF electronics that kind of demonstrate the breadth of research going on in engineering in MR. So for those of you who don't know, MRI is one of the most powerful clinical tools available today. If you come into a hospital, chances are that you will end up in an MRI machine at some point. In fact, if they did a poll a few years ago, this is 2001, where they asked a whole bunch of physicians, what's the most important invention over the last, I believe it's 50 years or 25 years. And the number one thing they came up with was MRI and CT. And given that this was probably a whole bunch of white men, the fact that it beat things like Viagra and balloon angioplasty is kind of impressive. But anyway, this is truly an important field. It impacts all of our clinical medicine today. Cleveland, for those of you who don't know, it could be called MRI City, USA. It's one of the first MRs in a clinic, was down the street at the Cleveland Clinic. First modern generation magnet was across the street at UH. The number one textbook was written by Bob Brown and Mark Hakey over in the physics department. I've actually recently just found an unauthorized version of this book in Chinese. It's literally the top book. But besides just this very local area, the MRI industry in the U.S. is concentrated here in Northeast Ohio. Philips has their U.S. headquarters out on the east side. Hitachi's down near Twinsburg. GE has a huge plant in Aurora. And both Toshiba and Siemens have opened up small shops out in Mayfield Village. So this is a huge employment force in this area. I stay in MRI, and I've been in this field coming up on 20 years because it's probably one of the most interdisciplinary fields I can think of. And I learned my basic knowledge in a lot of fields through its application in MRI. So for example, physics, you can learn about quantum mechanics, electromagnetics, and computational physics through their use in MR. Engineering, we use digital sampling, RF engineering, which is where I got started actually, low noise design, parallel computation. Then the more obvious ones like medicine and biology, molecular biology, all of these play a role in MRI every day. And so you can really, I can be a physicist one day or an engineer another day, I can play doctor and just, move back and forth between them pretty easily. So in my mind, there's lots of good reasons to learn about MR technology. So just a quick few-minute intro into MRI, how it works, so that we can understand the more advanced topics to come. MRI is based on the nuclear magnetic resonance phenomenon. We can use this phenomenon to measure almost any physical property of any material. For example, it's used to determine chemical structure, was where this really started. And then in the form of MRI, we use this to study all kinds of diseases. And over in the clinic, this is by far the most complicated imaging modality that's over there. So it takes quite a few years to really learn this in depth, and we're going to try to do it in 5 minutes. So MRI is based again on the NMR phenomenon, and it has this word nuclear in it, so it has to do with the nuclei of atoms. Many of them have a property of, or all of them have spin or angular momentum. And for some particular configurations, they also have a charge. And this spinning charge creates a magnetic field, which I'm going to represent by these little red lines. So normally we can't observe this magnetic field because at room temperature, all of these little magnetic dipoles are oriented randomly. But if we apply a big external magnetic field, all of these spins will align themselves either along or against the magnetic field. And there'll be a slight difference in states because of the energy difference between going with the field and against the field. But this difference is really small. It's about 1 part per million. So 1 proton is flipped up where it should be flipped down out of a million, which is really, really small. And it's that difference, small difference in states that will combine to give us essentially a microscopic magnetic field that we will use for all of our imaging. So quantum mechanically, this will be a 2-state system, and I'm going to go through that. Classically, this is just this composite magnetic field. So this is shown here. So in this quantum mechanical system, this is really similar to chemical bonding or fluorescence. We put some energy in, the spin relaxes back down and emits some sort of energy back out, which we can then receive. So the energy difference between these 2 states, again, is very small. It corresponds to radio frequencies. And the energy or the frequency of this difference is given by gamma V0, where this is our applied field. This gamma is a property of the nucleus itself, and it's different for each type of nucleus. For protons, which is protons of hydrogen, which is what we typically use in MRI, it's 42.5 megahertz per Tesla of applied field. And for a 1.5 T field, which is common in the clinic, that's about 64 megahertz, which is between channel 2 and 3 on your old analog TV. Won't be able to use that analogy for too much longer. So to get this radio frequency energy in and out, it's just exactly like an old analog TV. We use something similar to an antenna to excite the system. We put some energy in, it gets us our transition, and then relaxes back down. And this relaxation back down is slower than the excitation, so we can observe this almost like hitting a bell. You whack the bell, you hear the ringing for quite a time afterwards, and this can go on for seconds. This is about 2 seconds here. And we basically receive this signal, and this is what we're going to use to form our image. So that was the quantum mechanical description. Classically, this is a spinning bar magnet, and the speed of the rotation is exactly equivalent to this energy difference. So this spinning field, through Faraday's law, induces a voltage in our receiving antenna, which we can then amplify, and again, it's exactly the same. So there's our signal. Just a quick word about SNR, because this is going to come up throughout the talk. Again, since we're only dealing with a part per million polarization level, we have very low signal available to us. And in this case, like it or not, the noise that we've got in the system is Gaussian, which is nice because we know the behavior. But now we have a firm link between the scan time and the SNR. So the longer we scan, the higher the SNR we get, but it's a horrible scaling law. So if we double the amount of time we scan, we only get square root of 2 better SNR, which is not great. But worse is if we want to go to increased resolution. So let's say we've got a voxel or a volume element that's 2 by 2 by 2, and we want to go to 1 by 1 by 1. So that's factor 2, factor 2, factor 2. That's 8 times smaller voxel. So that's 64 times longer scan time to maintain the same SNR. So if we had a scan at this resolution, which was 1 minute, to get the same SNR at this resolution, that's an hour. So for those of you who've sat in the horrible caged environment of an MRI, this is not the kind of scaling law that you like to hear about. So clearly, going faster at higher SNR are the big challenges that are still with us in MR. But first, how do we get, or how do we tell where the signals are? How do we do actual imaging with this? So how do we tell the signal from this part of the head, from that part of the head? And the answer comes from, again, let's go back. The frequency of our precession of this spinning magnet is proportional to the applied field. So Paul Lauterbur, way back in the 70s, realized that, well, we could linearly adjust this field by applying a gradient. So it's a field that depends on x. So on that side it's weaker, on this side it's stronger. If we do that, then the frequency of the precession of these little bar magnets is faster on one side than it is on the other. So just do this again. This corresponds to our excitation, and then the precessional frequencies are different between those 3 positions. So in a way, what we're going to do is we're going to differentiate those three positions exactly like we differentiate three musical notes. So the three protons in that case are going to each have different frequencies. It's like hitting three notes on the piano. What we observe in our raw data is the sum of these. And then hopefully, for those who have had signal processing, you could do a Fourier transform and pick these apart. So now we would get three signals which correspond to the three different frequencies there. And now we essentially have an image. We localize the signal from those three spins to their three locations. So that's just a one-dimensional experiment. In reality, we have to do a three-dimensional experiment, and it gets somewhat complicated, but I'm just going to say that we magically have three gradients, x, y, and z, which we apply in the right way. We collect a whole bunch of raw data, assemble them now into a multi-dimensional Fourier transform, apply the Fourier transform to that data. This is a multi-dimensional Fourier data space. We Fourier transform and get our image. So this is, again, is the data that we're acquiring in MR. And again, just another note, that should have been a whole semester, and now we'll do another semester in a single slide, just to go over the kind of range of technologies that we have in MR. So if we start with the big magnet, and pull apart all the different systems that I've just talked about, we have a big static magnetic field, which is what we use for our polarization. This is in the range of 1.5 to 7 Tesla, so hundreds of thousands of times the Earth field. And it's static, so it's part per million homogeneity and part per million change in time. Incredibly stable. Inside this is a superconducting magnet. There's anywhere between 500 and this is a little bit old slide. There should be about 2,000 amps in some of the higher end ones. So this is really a complicated device. We have these gradient fields, which are the fields that we use to do our encoding. These are in the range of 10 to 100 millitesla per meter, and they now have switching rates in the audio range, in the kilohertz range. These guys are driven with amps, with 500 amps, 2,000 volts. So that's a megawatt peak per axis that we have in our current system today. Finally, one layer in, we have our RF fields, which we use to excite and receive the signal. These are on the order of microtesla fields, or 10 to 100 microtesla field. Their megahertz range anywhere from 8 to 800 megahertz. On the transmit side, we require quite a bit of power. It's kilowatt power levels going in, and the power that we receive is incredibly small back. It's femtowatts to nanowatts in a good day. So it's just would you like to work in the low power or the high power regime, low frequency, high frequency regime? We have the ability to work on any kind of electromagnetic engineering problem here. It's really fantastic. So I've got two topics for today. One on how to speed up imaging. Again, this is this topic of compressed sensing. And at the end, I'm going to spend a little bit of time on increasing the efficiency of excitation using a concept of parallel transmission. And we've got a lot of other research projects going on, but I chose these two because I think they're the most general for what's going on over here right now. This compressed sensing, I think, I'm going to show you it in the area of MR, but I think it relates to all digital signal processing today. And the parallel transmission stuff we're doing here is exactly what's happening in wireless and cellular. For those of you who are doing MIMO research or whatever, it's exactly the same. We're just doing it on a much smaller scale. So let's go back to this spatial encoding. This is one layer more of detail than what I showed up till now. So what I've shown schematically here is a gradient waveform in time. So at this time we apply a negative gradient, and at this time it's a positive gradient. So when we look at any one particular time on this gradient, the Fourier component that we are sampling at that time is given by the time integral of that gradient. So we start at 0, and let's just say that this is height 1 and this is 128 microseconds. That would correspond to k of a minus 128. We switch it positive, we go back through 0 out to 128. And these are just the Fourier component that we're sampling. So in time, we would play out something like this with the gradients, and then typically during this part of the gradient waveform, we would sample the data, we would digitize it, put it in our Fourier space at the location denoted by k, which again we can get from here. So if we look at this then, and when we think about speed, it's the area, again, at any one time, the time integral up to that point that gives us the position in this Fourier space. So if we look at this then, the speed, the velocity at which we're sampling this Fourier space is proportional to the strength here. So the stronger the gradient, the faster the sampling that we can do, because again, it's the area that matters. So the area of these three are all identical, but this one is much faster in time than that one. So a lot of the work starting in about 1988, going through till about 1998, was on making these gradient systems faster. These are essentially just big inductors which are configured in the right way to make this change in field from left to right, for example. So in the early days, these were about 10 millitesla per meter on all three axes, and it took about 1 millisecond to switch them to full field. This, I believe, is the strongest it's ever been used on a human. I was in the system, unfortunately. It was the strongest ever used, I believe, in 1998, which was 50 millitesla per meter and 60 microsecond rise time. And so these are just dramatic improvements over those. But that was 10 years ago, and I'm saying that's the limit of what the field was able to do. And why haven't we gone further over these last 10 or 11 years? And what it comes down to is you hit a wall very quickly. So again, it's the area that matters in our encoding. So if we want to do a factor of 2 faster imaging, we need to turn that gradient waveform into that one. So this is half the time. And what that means is we need to get 2 times greater strength, but also this ramp is 4 times higher. It's got to be 4 times faster ramp. So what we realize is that we quickly reach the limits of what we can build on one hand and what the patient can tolerate. So these switching waveforms can stimulate the patient, which I'm not going to spend a lot of time talking about, but this is a real safety problem. But let's just look at it in terms of the gradient amplifier. This is what these gradients look like. They're just loops of wire. I can show anybody who's interested later. It didn't really turn out real well. But okay, so we said the rise time has to go up and the strength has to go up. So this rise time is proportional to the voltage that the amplifier outputs, right? If we just write down the current equation for an inductor. The strength of the magnetic field is proportional to the current that's running through the inductor. So let's just look at power. So if we want to go R times faster, that means R squared higher voltage, again, because it's got to go with the square of the speed up, and R times higher strength. So that means the power goes with the Q of however fast, whatever speed up factor you want to do. So again, over across the street, we've got 2,000 volts, 500 amps. That's 1 megawatt per axis, 3 megawatts. That's equivalent to the whole front row in a Formula One race, just to be clear about how much power we're driving around. This is a huge amount of power. So if you want to go 2 times faster, that's 24 megawatts. That's what they're talking about gathering in all the wind farm out on Lake Erie, right? 1 MRI unit. If we want to go to 4 times faster, this is 192 megawatts, and we start needing one of these just to drive an MRI. It's just not going to happen. Talking about healthcare reform. So it's clear that we need something different, and that we've really hit a technological barrier here. And the other side note is that every 2 times improvement in SNR or speed is really a big deal. You really have to fight to get that with conventional means. So I hope to show you that we were going way beyond this, and it was just a dream 10 years ago that we could do this kind of stuff. So let's go over the Nyquist limit, basic fundamental stuff, because again, we're dealing with a digital system here. Let's talk about what we need to do here. So this is the limit that he established back in 1928, and in my field, as in yours, it's basically religion. And it says if we want to image with a digital system, image volume with n cubed voxels, then Nyquist God says, thou shalt have n cubed samples. And there's no way to get around that, right? So that was true until these guys came around, really. This is Emmanuel Kendez. This is from his paper in 2005, and what they said was really groundbreaking. And these are math guys. All 3 of those authors are math guys, and they I think part of the reason this paper was so important is they immediately recognized the importance of what they had proven. And what they proved was that the number of Fourier samples to get an exact reconstruction is not dependent on the number of voxels or the number of target samples. It's instead related to the number of voxels containing information. So Nyquist derived his theory based on Shannon information theory. This is a complete breakaway from that, but he's still using the word information here. But in this case, it's very different. And I don't know why these are showing up so poorly, but if we look at this example, this is our target, which was acquired with 400 projections that should read. This is our perfect reconstruction. If we drop this down to 20, this is all aliasing because now we have not sampled the Fourier space densely enough. So we have all these aliasing artifacts. But if we take the reconstruction from this theory that they came out with in 2005 and make the assumption that there's only a few pixels with edges, in this case was the assumption they made, they can get a perfect reconstruction with only 20. So this is a factor of 20 improvement over what Nyquist would say. This is a big deal. Again, a factor 2 is a big deal, a factor 20 is an even bigger deal. And so what this means is that we can change our scanning philosophy we're not scanning for pixels anymore, we're scanning for information. And this is, again, a 3, 4, 5-year-old theory, and this is really going to change the way we do a lot of things. So our acquisition goals are going to be to collect only the information that are needed, and that the scan time in that case then is no longer proportional to the number of pixels in the image, it's proportional to the amount of information. And so we want to combine the data in an optimal way to get just the info we need. And when we combine that with an optimal acquisition, we can go much, much, much faster and also potentially much higher SNR than any of those traditional methods would work. So let's just go through a simple thought experiment which should show us why this would work. And it's really pretty simple. So let's assume we've got several interesting pixels, in this case 3, in our field of view. And let's just assume that our digital matrix here is 100 by 100. So we would need 10,000 samples normally, right? Let's assume that these 3 pixels vary with one dynamic time course and that we know exactly where they are. So the question is, how many samples do I need to get an exact image reconstruction? Does anybody want to take a guess? 10,000? We need 1, because they all vary exactly the same way. So I literally just need to turn on my A to D converter, measure the data, I know where the pixels are, and I know that they're all the same, and so I just have to reassign that signal to those 3 pixels. And under these assumptions, I've done a full resolution image in a factor of 10,000. And that I could make it a factor of 1,000,000, you name it. We've named this the Hennig limit after the guy who kind of came up with this thought experiment. But in reality, we can't always assume, this was an extreme example, and the reason is that we can't always assume that we know where everything is, and we can't always assume that they all vary the same way. But we can get pretty close to this, as I'll show in the following slides. So there's kind of 2 approaches to solving this problem. The pure approach that Kendez and following Mickey Lustig came out with directly solves for the interesting pixels. So they don't assume anything about the image, and they just directly solve for that. And computationally, that's a pretty challenging problem. What we're working on in MR is an approach that we can hopefully measure where these interesting pixels are, and then the only problem is solving for what their intensities are. So I'll come back to that in a second, but I just want to make a link here to the generalized sampling theorem, which dates from the late 70s. So Fourier said, if I have a signal with the bandwidth of f1, this is a spectral domain, then I need to sample at 2f1 to be able to fully resolve that signal. Papoulis in 77 came out and said, well, wait a minute, we can do bandwidth undersampling too. So if I have a finite bandwidth of width f1, regardless of its center frequency, I can sample at 2f1 and still reconstruct the signal perfectly. Right? So I could have a bandwidth of 20 gigahertz, and as long as this is still 100 kilohertz, I only need to sample at 200 kilohertz, assuming that A to D still works at that rate. Okay, so this was already, a big leap in thought. And in my view, compressed sensing is just a similar kind of thing, but instead of having a finite contiguous bandwidth, this bandwidth is broken up into pieces now. So I've got pieces where there are interesting spectral information, and regardless of the full finite spectral width here, as long as the sum of all of those interesting spectra are equal to this F1, we can sample at something close to 2F1 and still get a perfect reconstruction over that whole spectrum. Now again, I may have to make some assumptions about where those are, but the information content in these three schemes is the same. So theoretically, I could reconstruct them and acquire them all at the same frame rate or the same data acquisition rate. Just we're going to end up with much more complicated processing here than there. So again, the way we're going to do this in MR, at least in my group, is we're going to divide the acquisition and the reconstruction processes into two questions. The first one is where are the interesting pixels, and the second one is what are their intensities at any one time point. And I like dividing the scheme up into these two questions because the time scale that we need to answer these two questions is dramatically different. The question of where the interesting pixels are, I can answer that very slowly. I can answer that over minutes to hours, whatever. But for a lot of applications where I need to know what is their intensity at any one point in time, that one I may need to answer on the time scale of milliseconds. But by dividing these, the acquisition and reconstruction processes into these two questions, it's something that I can potentially answer. If I just blindly did this in the old school, again, there's no way to do this. The other nice thing about this is that it potentially disconnects this link that I talked about at the beginning between SNR and imaging time. It may be, and we've shown actually, that we can get SNR on a very short time scale, but proportional to this time scale. So we can acquire data over 5 minutes and preserve that 5-minute SNR independent of how quickly we reconstruct the frames inside that 5 minutes. And again, this is something that was impossible just a few years ago to even imagine. So I've kind of talked around this, and I'm not going to throw up equations today because it's the first day of school for me. But just in general, all of these methods depend on sparseness. And sparseness in my world means that there's only a few pixels with signal that I care about, or a few pixels with changes in signal. That's what sparseness means to me. There's also this concept of transform domain sparse. So it could be that I can apply some sort of transform to my data, and only a few of those coefficients are relevant. So I could wavelet decompose the image and say 10% of my wavelet coefficients are relevant, all the rest are 0. That's a possible. Or going back to the original Pandez paper, they assumed that there's a small amount of total variation or a finite number of edges in the image. So all we basically have to do is get the problem into any one of these states, and then everything that I talked about applies. And I just want to go back and highlight that if this spectrum is dense, right, if there's important information all the way across here, I can't get any savings in time. I have to sample the full bandwidth. This is only going to work when there's only sparse data or sparse information. Okay, then I can potentially save time.
Does that happen often?
We can make it that way. That's the point, I guess. So, you guys surf the web, so you guys have downloaded JPEGs, I assume, a few times, right? That's much faster to download than a TIFF, which would be, dense. A TIFF is every pixel, just one number after another, right? But we know that images that we look at with our eyes are compressible in that, there's only a few wavelet coefficients or a few DCT coefficients that are relevant, and we can just set the rest of them to 0. And so, that's what we would just call compression, right? This is compressive sampling. So we're assuming that the final data can be compressed. And so if we can sample just those coefficients in the dream world that would fully represent our image, then I don't need to collect, the TIFF image in between. I don't need the full bitmap in between. So that's kind of the shortcut that we're taking. So, you asked, does this happen a lot? I think for every image that we view with our eye, It happens quite a bit. And hopefully, especially when we get into the finite number of changes or this total variation type stuff, in particular for medical images, those are going to be really relevant. So here's a simple example of how we can basically make this happen. So let's assume this is going to be a time course, and up here's the full data, and I've undersampled it by a factor of 4 here, so this is aliased by a factor of 4. Every pixel is sitting on top of 3 others. So if I go through and these 3 pixels here have changed in intensity, I can resolve that here, and down here I still can't really resolve it if I go that fast. But now if I subtract them, if I assume that the differences in time are small, I subtract that frame from that frame, now there is no aliasing in a formal sense here. There is no overlap of information between the different pixels. At this point it's just a selection. I just need to select which of these copies is the right one. And if I know that this is the relevant chunk of the image, then I can exactly replicate that 4 times faster. And in this case, given the sparseness that's here, I could go even faster. So again, this is just a schematic version of that, how we could go 4 times faster. And again, if the image is dense, if the image is all changing, we can't do this. This is relying on the fact that there's just a few pieces of information that are changing. So one problem where this is really relevant is angiography. So this is where we're trying to look at the arteries and the veins in the body. The way this works is that we inject a drug that we can see in the MRI into a vein. It then travels around, and hopefully what we see first is the arteries and then the veins. But we have to scan fast enough that we can separate those two. Eventually, if I wait 10 minutes, the whole body's going to be at equilibrium, and I can't see anything. The other thing that's important about this, so I have to go temporally fast, but I also have to go spatially very high resolution. I need to see vessels that are on the order of a millimeter. And so that's a very, very high resolution scan. So again, this is where we're running into that trade-off between SNR and imaging time. So if we do it right, this is the kind of thing that we should see. This is in a head. The person's head is looking exactly this way. The contrast agent should come in, and then it should flow around, and then flow out. And this is the kind of thing that we should get. But what you can see here is that this is kind of sparse. There's only a few pixels that I care about, and this is actually a full 3D data set. So when you piece this apart in the 3rd dimension, it's even more sparse. So again, in this application, we can't assume that only a few pixels have signal. And in this case, remember, we're answering those 2 questions. Where are the interesting pixels, and what are their intensities at any one point in time? So we answer the first question by just gathering up a whole bunch of data. So we take, in this case, the data over about a minute and just sum them together. And from that extended acquisition, we make what we call a composite image. And then what we're going to do is a pretty straightforward application of the generalized sampling theorem, or that compressed sensing scheme that I showed there, by using this as a mask to tell us where the interesting pixels are. And we can't do it exactly like what I showed there, because a hard mask is in a way too hard for real MR data, which is noisy. Areas with low signal or low SNR would just disappear and they would never come back. And we have to mess around with a lot of regularization parameters if you do a hard mask. But what we've done is a soft mask, so we use a composite, but we allow some level of signal to appear in those regions outside the mask. And then we use this as a weighting in an iterative scheme to basically drive the solution towards the correct one. If anybody wants more details on this, I can do this. But essentially, we're solving that generalized sampling theorem problem using conjugate gradients with this composite image as a mask to tell us where the important information is. And we call this GST-MRA. So this is a real application. So this is 192 by 192 by 15 in the 3rd dimension. And each one of the images you're going to see was reconstructed with 15 projections per in-plane image, which is a factor of 20 compared to what Nyquist would say. And again, we generated the composite from all the projections, and the mask was 10% of the maximum, everything over 10% of the maximum value. So this is what we would get, this left column is what we would get if we just did plain simple Fourier transform. It's this non-uniform fast Fourier transform, but essentially you should view this as the FT of the undersampled data. You can see that there's a lot of what we call streak artifacts relating from the undersampling, and they're very noisy. Can't really see much. If we just mask this, again, it doesn't help a lot, it just looks bad. But if we follow this iterative procedure based on the compressive sampling, we get something which looks very pretty. So this is the contrast agent just coming in, spreading out, filling in the vessels, moving on. And this is at a level where it's just on the edge of being diagnostic. This is something that could be translated in a very short amount of time to the clinic. And each one of these now is a whole volume being acquired in about 200 milliseconds. So this is really fast data. We can look at this in a relatively quantitative way too. Look at the arteries and the veins. If we just do the Fourier transform, that's these dotted lines. It's very noisy, and in particular this venous signal is just wrong. The solid lines are what we would expect. You see it in the artery first, and then at some point later you see it in the vein. This is what we would expect. So compressive sampling in MR, just to sum up this section, the scan time and the SNR going forward are proportional to the number of voxels containing information, not the number of voxels itself. This is a big change in philosophy. And again, we're going to have dramatically increased speed in SNR. What we need today, faster computation. We're talking with several people over here about GPU implementations, higher accuracy. Can we do this faster and better? And we need, this is something not to ignore. We need to know how wrong we are. And this is something that's not possible with really any of the current methods out there. We don't have a really good idea of, is this image good or is it bad? And this is going to be a topic of increasing importance in the coming years. So moving from compressed sensing to this parallel transmission concept, I just want to go back, and this is a recurring theme, but MRI is really insensitive, low SNR. And I talked about ways that we can potentially address that through better sampling. One of the other ways that we could do this potentially is by going to higher magnetic field. So instead of 1.5 T, people are going to 7 T and above. And so what that gets us is a higher field, higher polarization, and potentially higher SNR, right? If we go from 1.5 T to 7 T, it's almost a boost of a factor 4. The problem, though, is that the body is a dielectric, so we're basically salt water. The mean dielectric constant is about 55 or 60, somewhere in there. And so what happens is the wavelength at these 7T field strengths and above starts to approach the dimensions of the body itself. So I didn't really talk about it before, but at these lower fields, at 64 megahertz, it's a 4-meter wavelength. So nothing in our body is particularly going to act like a wave. We can assume it's quasi-static, and just the electromagnetic energy is going to propagate through. But at these frequencies where the wavelength is 11, 12 centimeters, now we're getting internal reflections inside the body. And what this does is create hot spots, a bright signal, and I guess even worse are these areas where there's signal nulls. So, if you can imagine if you've got a tumor there, you may not even see it because it may not even be excited. This is a real problem. So this has prevented us from realizing the higher SNR possible from these higher field strengths. So there's been a lot of studies out there over the last 5 or 6 years which have shown that if we can control the current in our excitation antenna or excitation coil directly and locally and on a patient-by-patient basis, then we can potentially eliminate this problem. But what this requires then is a parallel or multi-channel transmitter system which would consist of multiple current sources on a surface. This is, again, related. You can see the link to cellular telephones, right? We're putting multiple transmitters and sending multiple streams of data to each phone. And if we can realize this will be a solution to these problems at higher fields. But what we need to do is look for a transmission element that fits all of the criteria that I'm going to go through here, and this is not so simple. So if you just kind of blindly do this, and this is what people have done over the last 5 years, this is what you would do. You would take your single channel transmitter system, which consists of a signal source and a power amplifier, which again is in the kilowatt range. You'd run a power cable into your room here, and then you would have to have some sort of matching element to your antenna or your coil here. So the problems with this is, first off, it's really expensive. You have to synchronize now all these high power amps, which is not terribly simple. Again, at the ppm level, you have to synchronize them. These cables now are carrying kilowatts of power at RF energies, so they're very expensive. Each one of those is about $10K in our current system, $10,000. And each coil has to be tuned and matched separately to each patient. This takes about a minute per channel on our current system, and you don't even notice it right now because it's just when you're being put in the scanner and nobody notices this 1 minute of adjustment time. When you have 32 of these and you're sitting in the magnet waiting for 32 minutes for it to adjust itself, that's not really practical anymore. So this is what's been limiting it. Finally, you have the coupling between these elements, that they interact with each other, and that causes all kinds of problems. So what we've proposed to do is to change the system from there. We convert this amplifier from a voltage mode, high power amplifier, to a current mode amplifier, and we incorporate it directly on the coil so that we can remove the matching interface elements. And additionally, we can then drive this with a low signal digital source and send it in over a fiber into the room. So this is hopefully cheap and better. But we need to talk about efficiency though. Let's just say we blindly do this. And let's say we do it with 15 kilowatts, which is what we've got across the street, and we do it with a Class A linear amp. And this is Dr. Laparo getting his MR scan, and he's happy. You just got your feet in the scanner, so you're happy today.
Okay.
But if we do this with a linear amp, we have at best 50% efficiency. So if we need 15 kilowatts of power to do work, that means we have to dissipate 15 kilowatts of power in the magnet. And so instead of it being a happy thing like this, he turns into this. This is a really good oven. So that's clearly not going to work. So one of the biggest things that we've done is really concentrate on the efficiency. So we've gone to this configuration called a current mode Class D, which takes advantage of zero voltage switching. So it's a switched amplifier, and the amplifier only switches when the voltage across the FET is zero. So there's hopefully no loss in that. So we have near perfect power efficiency, and we also have reduced load sensitivity and decoupling, as I'll get into. But this is basically the configuration. We've got two RF FETs here. We have an output filter, which we designed, and this is our coil here, which is a series resonant circuit. Power supplies at the top. And then operates like this. We turn on one of the FETs, turn off the other one. So this one just experiences its on resistance. Well, this is the drain source capacitance of the off resistor. If we look at that and we assume that the R-on is very small, we make that the output filter resonant with that CDS. These essentially look like this. So we've got a short on this side and an open on that side at the RF energies. So our current flow is like this. So this gets us turn on the gate, get the half wave on one side, it's a bridge, and then we just go on the other side and switch that back and forth. And again, if we assume that R-on is very small, we have a pretty close to a perfect amplifier here. So I just quickly want to talk about isolation too. So whenever we've got two of these high power amps next to each other, we need to make sure that they're isolated. One of the problems is inaccurate excitation problems, but there's also this requirement to sync anything that comes in from another amp. So if we transmit some signal out to that coil, to make its local field here, if some fraction of that energy is coupled over to this coil where there should be none, for example, it will also make a field over here, but more importantly for the hardware, that power, some fraction of that power will also get transmitted towards the output of the neighboring amp, and that amp would have to sync it. Not only would it have to sync that power, but generate whatever power it's supposed to generate. And so, again, if we have 32 of these, you can imagine that the power requirements here for these amps just goes through the roof just to deal with this. coupling issue if we don't have some way of dealing with it. I'm going to come back to that in a second, but this is a very simple version of this. This was the first version that we did. Just to show, we have our digital signal coming in here. This is a gigabit Ethernet, can't think of the word, just like a gigabit, sorry?
Transceiver?
Yes, thank you. Just like what you would use on your gigabit Ethernet connection today. Standard Ethernet fiber to another transceiver, and then just a short run to the amp, and here's our coil, which we're actually going to use for our excitation. So when we put this current mode class D, since it's got that resonant output filter, what we actually see is a very large impedance to any current that's trying to come in from the outside. So this is a comparison between the conventional resonant coil that I showed in the beginning to one with this current mode class D amp. This is just an S21 measurement showing its resistance to current from the outside. It's about 25 dBs, which is perfect. But in addition to excluding those currents from the outside, I don't know why it's switching, but we also then end up with load insensitivity. So here we've taken a bag of saline basically and placed it at different locations or different heights away from the coil. If we have a voltage mode device, the current that we see, the B1 field that gets generated by that coil, is going to depend heavily on the load, right? It's a voltage mode device. On the other hand, if we have a current mode device with a high impedance directly at the port, we inject exactly the right amount of current over a very broad range, and we've extended this down over to here. So it doesn't matter what you put in the magnet now. Now we don't need to do that adjustment at the beginning. Just put the patient in the scanner and go. We don't need to worry about anything. So on the bench today, we've got 2 kilowatts out of each of these modules now. High efficiency, bordering on 98% in some cases. We've got high isolation. I showed you 25 dBs. We can beat that. We have fiber optic drives, and we have the load insensitivity. So we believe that this is going to be the future of parallel transmission arrays, and we're working with a lot of people to make that happen. This is just an example of our first prototype that we built, which was a 4-channel prototype. So you can see this is one image in the middle, and this is an image from each of the 4 independent elements. And you can see that for the element over here, it doesn't appear to be seeing any of the other elements. It's just as a monotonic decrease from right to left. Same thing here, bottom to top, maybe a little bit of coupling there. But essentially this is working well independently, and then when we combine them, we get a very nice homogeneous profile. This is exactly what we want. So the open problems here, I don't even know how to define the efficiency in a system like this accurately, because it's a non-50 ohm system, and what we actually care about is transferring the power from our DC supplies to current. And so there's not really a definition for this kind of amp. We're working on defining that right now. I didn't talk about it. We also have a current feedback system to ensure that the current that we put in is exactly what we measure, and we're working on making that a fiber system right now. And finally, the biggest limitation for us right now is constructing this digital synchronized source. So we have 32 to 64 digital signals that we need, and our transmission protocol right now is signal delta encoding, which is about 500 megabits a second output that we need. So we're looking at FPGAs and all kinds of different things to output that data. So just to sum up everything I talked about today, even though MR is 25 years old, maybe even a little older, it's still growing. I don't feel like we're anywhere near the end. And again, I think it's one of the most interesting, interdisciplinary topics that you can get involved in, and you just happen to be sitting in one of the centers of its development worldwide. I think we have a bright future in compressed sensing. This is going to be true across all the digital processing fields that we're doing. Faster, higher SNR, better across the board. And parallel transmission, I think we could easily transition this to a high power cell phone antenna or you name it. They're all going to have similar properties. So lots of work still to be done. I want to thank my whole group across the street, and in particular these 3 folks for slides, and Dr. Leparo for inviting me over. Thank you all for your attention.
Well, I definitely think we have some time for a few questions. So, any questions for Mark?
You mentioned that you, in the comprehensive sampling, you use, or you're looking for interesting pixels, and then you also are interested in intensity of the pixels. In the method you showed later, it seems to me that you use the current intensity or intensity whatsoever in order to find the interesting, to trace them and find the interesting pixel. So you mix the two, or how does it go? And is there any other method to identify interesting pixels, the sparse interesting pixels?
Yes. So to the last question, definitely, but they all involve looking in time in some form or another. So each one of the pixel, or each one of the dots on this graph from here to here to here is about 200 milliseconds or 300 milliseconds apart. They're not labeled here. And we need to see them on that time scale so that we can differentiate this yellow curve from this red curve, okay? Yeah. But the way that we're doing the masking in this case is we're saying, all right, I don't care about differentiating the two. I just want to see where did something change over time. So I take all the data from this whole graph and can collapse it to one data point. And so by doing that, I get some signal from veins, I get some signal from arteries, and all in between. And when we put that together, then that gives us the locations of where interesting things happen. The intensity in that image, though, like I need to know that for this pixel, this intensity was low here, high here, right? And that identifies it as a vein. That's the question that we need to answer very rapidly. And that we can't do from that composite image, right? That's just one data point. So the two are linked.
Yeah.
But again, they're different time scales.
That's the pre-processing before you go to the compressed samples.
Yeah, I mean, I can take that data, and I mean, one grid is 5-10 seconds, something like that, for the 3D grid. Yeah. So it's, you know, that making that mask is very rapid. The individual processing of the individual frames can be minutes right now. The two problems are linked, though.
Yeah.
Another question? Ed?
So you've got one thing where you're presumably doing like the Fourier style sampling, where you take a long time and you build up this image of where your interesting stuff is, and then you're going to your different sampling mode and focusing on the details, essentially. Could you also like do like maybe a coarse, fast, like Fourier processing step, and like look for areas of the highest gradient in that, and then go back and use your faster stuff to build up the details in those areas?
The problem is that, so it's a great question.
I mean, I realize that you probably would lose some detail where your Fourier had low gradient, but could that give you more speed, is what I'm basically asking, to get an image with some detail?
So I would refer to that as adaptive sampling.
Okay.
So, you know, you're going to do some sort of coarse sampling, see where the interesting information is, and then sample some more.
Right.
Is that
basically, yeah.
roughly it? The problem is that we're sampling in the Fourier domain. And so all I can do is add Fourier components to the image, and in the image they're going to be global, right?
Right.
I can sample. I was drawing this over here, and I don't think there's any real way to show you guys that. Let me just. No, that's not going to work very well. I can add. I'm always sampling in the Fourier domain, and so I can add new information to the Fourier space, but it's not going to. I can't, for example, sample the left side of the image at higher resolution than the right-hand side, right? I don't have Fourier. Right. If it was a wavelet domain or anything like that that was spatially localized, I could do it. But I'm sampling in this Fourier space.
Right.
So it's global in the image.
So when you when you go to your broken up spectra where you're picking up more detail in each of those areas, how are you doing that? Are you actually changing your sampling in some way, or is it just a processing technique?
It's all post-processing at this
Okay.
point. It's all, let me show you precisely what I'm talking about. So I would collect the data, and it would have a bandwidth corresponding to this,
Right.
for example. So call it 100 hertz, just for now, right?
Sure.
I could reconstruct that 100 hertz bandwidth, and if my data comes all the way out to here, it's just going to be aliased by a factor of 10, say, right? What we're doing specifically in this GST MRA processing, which is just one of many, right, is saying I know that this portion of that bandwidth belongs there. I know that the next portion belongs there. Just literally, it's an assignment process.
Presumably, you have to have a high enough bandwidth sampler, like your actual sample and hold in front of your A to D converter, high enough bandwidth to cover that whole span.
Right.
Okay.
That's the only requirement. But that's typically, we're sampling nanosecond is your
Right.
sample and hold, if not faster.
Right.
So that is absolutely a requirement. But once you've got that, then you can do this. And so your first, just to be clear too, your first guess on this assignment of piecing apart that F1 bandwidth there is never going to be accurate. So you basically have to do this as an iterative process.
Right.
You can write it down as a matrix equation. We've got our imaging equation and our data, and we basically are chopping out rows. Imagine it's AX equals B, right?
Well,
And-
I mean, I'm assuming that's why you've got to do your sampling for a long period of time. If you've got bandwidth to here and your actual sample rate's, so wide, then you're going to have to build up for a long period of time to get that image that contains that whole span of stuff, right?
Right. Or we would have to know it from some other process somewhere else. But yeah, that's effectively what we're doing. Right? And then we know, okay, that is relevant, and so on. And then it's just a matter of solving the, AX equals B, where we've just eliminated rows and columns from the A matrix to solve for the B's that we've got, right? It's pretty straightforward at that point. It's just a question of the subtleties of how you define relevant and not.
Right.
This is just 1 or 0. What we do is we allow some small level of signal here and hope that the solution, this is all optimization theory at this point. So you hope that the solution converges to the right one. You hope that it has some sort of convexity at the bottom.
Right. Because presumably you're going to have some noise and stuff that's going to alias to everywhere else.
Right. Right. And you have to allow that, right? This is part of the subtlety of it. If you don't allow the noise to kind of sit out here, then all the noise for that entire bandwidth piles onto these, which is also not what you want. So there's a subtle trade-off there between enforcing the sparsity and then letting the noise be normal, what I would say.
I'd like to come back to something you mentioned at the very end. Your high current drivers.
Yeah.
Where's most of the power being dissipated?
Hopefully in the sample. So, which
Not in the, your superconductors are truly that good that.
oh yeah, they're very isolated. So there's an RF screen. So these are megahertz range. So there's a copper cylinder on the inside of the magnet which prevents any of the RF energy from getting into that supercon.
And the ESR of those inductors is small enough. The effective surge resistance is small enough that you're not really burning up power in the.
So the ESR of these inductors,
Yes.
the on resistance are the two dominant sources of power dissipation in the amp. But they're both on the same order as what we're dissipating actually in the patient. So it's a radio wave propagating through there, just like your cell phone. So we're propagating RF energy in. It's heating up the sample, and our goal is to make it so that is the dominant source. Right?
So efficiency is how much power is being dissipated in the sample divided by the amount of power that you're supplying from the DC supply.
it's power added efficiency, but it doesn't really, it's close to that, yeah. Normally this would be 50 ohms, and then everything's fine and dandy, and everything's matched, everything's nice. We don't really have access to this R, first off, because it's a patient's body, and we don't have a good way of measuring the R, and we don't have a real good way of characterizing the on resistance of that FET, because it's not constant in time either. It's just a very difficult problem to
We have a similar problem.
love to talk to you about.
Much lower frequency. Similar problem.
Yeah. I mean, we can't even really characterize what's the B1 field of this thing that's being generated fully, right? Because it's spread out over a whole range of spatial positions. We can estimate it. We can estimate the current which is flowing down this leg. We can kind of estimate the loss that's in that on resistance, but the on resistance of the FETs that we're using is like 0.1 ohms. So you put any kind of measurement device on there, you've just screwed up your efficiency by a factor of 2 or 3. And so that's the problem. Yeah. So we just say it's very high. we say we can touch the FETs when they're on at full power, 50% duty cycle. When we've done that, it's high enough. Of course, IEEE won't publish that at that level. If you have any clues on how to,
We're struggling with a similar problem.
yeah, it's not simple.
So these multi-kilowatt RF amps, are they on the whole time the patient's there, or is there a duty cycle to these things?
They could be on as much as 50% duty cycle.
Okay.
I mean, this is, if you go into a magnet today, and if you want to come over and experience this, I can put your whole body right at the FDA limit for heating. And
Will it warm you up?
oh yeah,
You can feel it?
oh yeah, it's nice in winter. Yeah, but this is a big limit in clinical MRI today. There's a limit, the FDA places on heating, 1 degree per 1 gram per 1 minute, and that's solid. There's no getting around that. And on the other hand, the more power we can deposit, it's the same scaling law. The faster we can go, the better quality of the images. And so when you get in that scanner, you are probably, depending on the exam, you are going to be right at that FDA limit or right below it most of that scan today. Of course, the efficiency argument is, again, that if we have to dissipate all of the extra power in the amp, which is not going to RF energy, that's when you start cooking people.
Presumably, this is also true of your coil drivers. They're going to be running at their megawatt levels the whole time, or like a 50. What kind of duty cycle do they have?
They're 100%. I mean,
Wow.
they're
Okay.
they're right peak.
Good grief. So you actually have to feed this thing that much power
Yeah.
the whole time the patient's in there. Wow.
Yeah. So the gradient amps are also a Class D configuration. They're actually very similar to this. They have to go negative. So there's actually, it's a full H bridge. They drive those with a megawatt. They're 95% efficient. That still means you have to cool off 50 kilowatts.
Well, and presumably your coils are just going to be turning it into heat.
They're water cooled right
Yeah.
now. Yeah.
Okay,
It's
Mark. Thank you. The sheet that's
Nice to see you
floating around
again.
You too, Chris. Really good to see you.